we started with the problem of nowadays we have a lot of AWS, GCP and all these things. In Flipkart, we were building our own data centers, like the cost versus what is working there, what is not working there. For a smaller companies to have handling like the cost versus AWS was cheaper for us. Like when we moved from AWS is less constraining because you can build a lot of things which will have ready-made tools also. But when you grow bigger and when you want to say have 1,000 developers, 1,000 people working on it or large number of servers, then they become costlier. And now coming to the scenario of if you want to do high performance computing on our own solution, like how we will be able to do it. That was the experiment which we wanted to do it in NEUU Labs. So we were getting billed a lot and said in NEUU Labs. So we said why don't we take all our servers into in-house and then see are we able to build the same resilience as AWS gives us. So that is the genesis of why we were building this. So we will take you through the step-by-step journey of how we built our own in-house solution of there and how are we able to even test solutions with LLMs with those kind of scenarios. So I have Pradeep and then Yogesh with me. So they are all the team guys who built these solutions for us in-house. Okay. So going forward, the key concepts which we want to cover over here is data center, LLM, multi-models, DeepSeek, so the different LLM models, containers, Kubernetes, and Olama, what is a gateway, what is load balancer, and what is the kind of RAG applications we can build with a minimal kind of a cost. Instead of looking one side, we said LLMs are very costly and how do we build applications around it. So here what we are going to look at is take a small kind of a data center and then try to see what all we can build with it. So the main concept is for us to see in an educational setup or inside the lab of a company, what all we are able to build in-house kind of stuff. So that is a concept which we started with and then we were working. So I'll take you through why we envision this data center is because we wanted to build data centers for small solutions for our own clients who are not connected to the grid. They wanted to use the solution end to end, work on it and deploy it type stuff. So we started with that solution. So I'll take you through the concepts how we each one of us is being manipulating and then how we finally ended up running our basic LLMs into the same data centers which we are trying to build. So basic architecture of a data center sounds very simple. You have to have a lease line, you want to have a static IP, and you have a kind of a firewall gateway and a reverse proxy kind of stuff. And then you have a bunch of physical machines, you have your Kubernetes cluster, you have your NAS solutions, which is S3 RAID, and then your data backups, what is the amount of data backups. So these are 4 different kind of solutions. One, you want to have databases or those kind of specific applications running on a specific machines. Those will come under the physical machines cluster. Then you have a Kubernetes cluster, which is you want auto scaling and all these kind of solutioning in place. So one cluster which will take care of that. And we also have why we have this active backup for mission. Gateway mission is if your single point of failure in your data center is going to be your gateway going down. So if the gateway mission goes down, you have to have a really immediately positive active backup, which can switch from the original gateway to the backup gateway. Then the third set of solutions is if every user I have to give them 1 GB of data for 1,000 users in my own organization, I need 100 TB kind of stuff, 1 terabyte is needed. If I have to give them each one of them 100 GBs, I need 100 TB. That's the kind of data we'll need. So for that, you will start with 10 TB kind of size. That's a minimum smaller one for us to run, right, and then take a backup and then run it. So this is for you to provide your users with a kind of a data which is secure, stored in your own place and also backupable and then data recoverable. So what we do is NAS softwares which comes with, there are traditional NAS softwares which we pay a lot, like 10 TB of NAS will cost you around 1.2 lakhs. So we'll explain you how we are optimizing on all those things. These are the 4 different general layers of the data center. So in the physical machines is where we will also start special purpose machines like video analytics machines. We have fine-tuned machines for certain purposes. Okay. So in the physical machines area, we have 3-4 different kind of stuff. So one is the raw machines and then special purpose machines. So low memory machines, which are useful for just using the data which is there in our database backups, the petabytes of data we are giving. It can be file storage, it can be logs, it can be emails, it can be caches, like any kind of storage, like photo storage and those things. So those will be served like a website, like a Wikipedia, media websites. They will be serving from the low memory machines. Then you have medium memory machines where you have like DB clusters which are running. So you have your master DB, slave DB, archival DB, and backup DB. So this is the kind of, these learnings are also, I'm taking it from Flipkart. Like in Flipkart, we have to build, because that point in time, AWS were our competitor, and we had to do all these on our own data centers, like the DB cluster, DB master slave backup at 2 different locations kind of stuff. So we are bringing this architecture from that setup and then also extend it to other needs of us. So shared GPU services. So what happens with LLMs is like a lot of times we don't need, everybody doesn't need the high CPU, GPU for training. You need GPUs to serve, that is lesser. GPU for training a model is different. So what we are optimizing is for serving a model using a GPU for a real-time application, like say 3 seconds to 5 seconds kind of a delays, like we have to respond to users. And we also have a large bunch of LLM based solutioning which you can do offline also. You can generate the solution and then send it to people. Like if you want to analyze a document, you analyze the document and send a report in an email. So that is the kind of LLMs which is much easier to do with a very small kind of a missions. Like, so that's what we will explain in that part of the missions. So this is the kind of physical missions. You have these categories, and you also have the other set, like which is like virtual machines, the applications like the microservices architecture, which doesn't care about physical machines at all. They are small services. They will run in 2 CPU machines. They can run, but you need a swarm of them. Like you cannot just do it 2 servers. You need 10 servers when you are in peak load. When you are in back night, you need small load. Like that is a standard scenario for any e-commerce, social networking, any kind of websites, learning websites, LLM. So educational websites, all of them have a peak load time, which is the evening time, and then the offices are over and those kinds of stuff. So that is where you need a scale up and scale down facility very well. So that will be managed. Not that managing it in physical machines is very tougher, very hard. Also, it's very resource intensive, and then you cannot respond it very fast. So for that, we have a bunch of Kubernetes clusters, which will have a master node, and you'll have a bunch of worker nodes and parts will be there. So what we will do is like we'll not have one Kubernetes cluster, because the Kubernetes cluster is your single point of failure. So you will have multiple Kubernetes clusters depending on the applications you would want in the same data center. So they will serve as a starting point. Also, they will serve as your isolation points. Like when something fails, that's only that particular service will fail, that network will fail, not all of them. So guys, like first one we would love to explain you is around the NAS architecture, like what we need for disks. Like when you want to train your data, you need a lot of data. Like so, what you have is like there are different kind of NAS providers. Okay. So you end up, what is the thing is like monthly cost, right? So if I have to serve a 12 TB data for my, let's say, like, let's take an educational institution where you have 1,000 students and then you want to give them like 10 TB, 10 GB of free space for each one of their code bases like GitHub or anything. So you will need like 10 TB of space for you to actually do that. So what we have done is like we have got an in-house QNAP solution versus AWS and the other Google clouds, what they cost. So they don't cost you upfront, but monthly they cost you. When you look at compare their costs of annual cost versus our cost, ours is like the total cost is around $200. Like when you buy it upfront, like 1,20,000 you pay, and then you pay $5 or $10 maintenance for your network. That's the only thing you pay, and then also a bit of power supply, and then you'll pay. But it overruns your cost of having the same amount of data in a cloud in 1 year. And most of these NASs generally work for 3 years to 4 years. So you get in 33% of the cost, you get the same kind of performance. And that's also in your own local storage, because your LAN, it will be faster. So whenever you try to download a large amount of databases, usually we face this problem in a company, like when a lot of new joinees are coming in, we say like set up your machine. So everybody will download 5 GB, 10 GB of data. That the whole day will be gone in just downloading, because a lot of people are downloading the same data again and again from the S3 setup in network. So it will be like time consuming for them. So when you are in LAN, all these things will become very, very faster. So, and also you have it in house. Like there are certain applications where, like government applications, say police security applications, where you don't want the files to be outside your network, but still you get the same kind of redundancy like which S3 provides or anything. Like the only thing it doesn't provide you is like what if the whole data center goes down? For that we have a solution around data center to data center data syncs. So you will have like data pipelines, and then it's an active, it won't be like active sync, but it will be active passive sync. Within 15 minutes of time, you will have both the data centers having the same 12 TB data replicated on both the sides. So that is the kind of setup you will be doing. So you can understand the cost savings which we will be doing by just start doing it in the space alone. Now comes the next part of the other part, like we'll go to each part and then do. So the NAS storage is the primary thing, is like you can have an infinite number of disks on your local and then save it. Like every time you will start saving a lot of money in terms of doing when you start doing. So next I'll take you to the load balancers, and this is architecture, why we need to set up and how we have to set this up for gateways. So the main purpose of these load balancers is like connecting your web services or microservices to internet and then serve them as maintain them against a domain name. So a lot of solutions are available for it. Like there is like hardware accelerated load balancers are there, software load balancers are there. So what we decided to use is like a tried and tested combination for Nginx. Like I've been using Nginx from my Flipkart days. It's around 15 years. Still, it's one of the lightweight and then most efficient in terms of doing this reverse proxy as well as acting as a file server and stuff. So I'll help you with this purpose. Like, so we have tested multiple things. Apache can be used as a reverse proxy. HA proxy is another open source project which can be used at it. But Nginx also can be used. But Nginx is the most resource efficient and then clean, and then also it comes with a lot of DDoS prevention methodologies on its own. Okay, so in ourselves, we'll help you how this works. Like, so basically, whenever you type any website in the server, you get a whenever you type a domain name in any of these browsers, you get to know what is the IP, static IP of the server from the DNS providers, like, and eventually that will land on your gateway machine. From the gateway machine, it has to get transferred to one of your web servers, and then the data has to go back, and then you have to have the SSL termination, your identity backers, and all these things. Because inside your network, you don't need all these encryption ones, because the encryption ones actually consume a lot of CPU cycles for it. So you don't want your local network to be with SSL certificates all the time, unless until you are signing it for somebody else. So what happens in this reverse proxy Nginx server is like it just runs as your web server, and it also terminates your SSL over there. Inside this, there won't be any SSL, because SSL will actually increase your load by 20-30% on any of this, like CPU consumption on the regular web servers. Okay, so not only Nginx doesn't provide one web server tracking. If you say like one website you can serve with 5 servers, it will also do load balancing of it. Nginx also helps us in load balancing heterogeneous machines. So in our network, we have 4-core machines, 8-core machines serving the same web server. We can say like machine 1, which has 8 cores, it will take 2x the load as one server 2, which is 4-core machines. So you'll have like hybrid performance and then reliability coming in from that. This is the concept, like all the clients will come, Nginx will take care of it and then serve it to next ones. So here we'll take you through the process of like how do we set up Nginx in a reverse proxy format. So basically it's a basic concept. So when you have an Nginx, usually you serve it and then you put your own location over there. Usually you put your file servers location, FTP location, or you start putting your general PHP or Python servers over there. Instead of it, what we need to do is like you have to proxy pass it to the microservice. So the microservice can be running in a completely different machine, or it can be running even in a Kubernetes cluster. So always you say that Kubernetes cluster host name and then domain name. So all these like host and domains is what something which is do. If you start using this method with one static IP, you will be able to serve like 10, 20 websites. Like we serve around 8 websites from our own single IP. So that is the purpose of this reverse proxy. It's not about just having, why do we need to have a reverse proxy when you can have a server itself? But you don't need to have everybody in a separate static IPs. They can be in the same server, serving from different sub-servers inside your gateway. Okay. Guys, if there is any doubts till now, you can ask me how this is going to be. Then we'll go into the next set of services, which is like EC2 equivalents and then those services point of view.
Yes, participants, if you have any queries, raise your hands. I'll enable your mic or give it in the chat.
So I'll proceed. No questions around it. Like, we'll just continue, guys. So this is like a basic set of services which can help you running web servers, the standard microservices and stuff. Right? We'll now go into the auto scaling process parts of the services, like how we are going to take care of that. Okay. So these are like the summarization of the cloud storage which we have provided. Hope this is not hiding your, is it hiding the text over there? Okay. So the difference between that kind of cloud storage is like seamless FTP. So cloud storage which we provide is like high performance, and then it's a private data center kind of a cloud S3 like. But what are the APIs we are providing on top of these services is going to be like S3. So you can actually do syncing between multiple buckets, those kind of scenarios. You can also start serving your websites and then photos from the same cloud storage. You don't need to have additional storage for it. So that is the purpose of S3 like cloud storage access. So you can have your photo gallery. It will be serving from the same photo backup directory which you have on your NAS kind of stuff. So that is the purpose of it. And you also have a bunch of data security things which you can do with it. And since it is your private data center, it's a data backup is also realized with you, and then you have hold of it. Like you don't need to, so when you are in say like when you're trying to download a large amount of data, when you say like 10 TB kind of a data, there is a lot of chances like the data pipe breaks, and then you have to make sure that is it all the 10 TB is downloaded or not. Those kind of checks and balances are becoming very easy if it is in a private data center, and then you have physical access to the machines. So then why do we want to do is like custom services is to support our initial team's access. So we started it our own troubleshooting and then setting up kind of stuff. Okay. So that is the part of storage part of it, like why we want to do it. And now comes the mission configuration which we are doing, GCP, what is the cost of it, and then tons of it, like say basically. These are the kind of different machines. So our data center has heterogeneous machines like low memory machines, medium memory machines, high memory machines, special purpose machines and stuff. So if you look at it, most of those machines like we break even very faster with them kind of stuff like the GPU machines and all. We'll be breaking even within 1 year, 1.2 years kind of a time frame. So that is a pricing point of view. And you also have your reliability onto it, like. So the GCP and all is like, it seems very low in terms of when you are using a smaller cores and then smaller machines. Like when you go to the bigger machines and bigger machines, your cost goes up. So the purpose of it is like the smaller machines cannot handle too much of concurrent users. Like when you have 20, 30 users, like all these low memory and medium memory machines will start failing in your service. So you end up doing is like minimum you will go for high performance machines or medium performance machines for you to serve the traffic. Okay. So This is about the configurations. Whatever you get in your local is kind of comparable to the costing of the other side. So now let me take you to the other part of it. Like if you have to do scalability, you have to do containerization of your code. So because you don't want your developers to go and say like today my scale will be 4x, so I'll have 4 web servers, tomorrow there will be 10. So we'll go to that containerization part. In containers, we have 2 open source solutions. Like one is like Docker based ecosystem, which is very strong, very there, but it is not very open source. It's not fully open source. You still have Docker support systems coming into place and stuff like that. But Docker is developed long back, so they have their own legacy problems, which are being eliminated in Podman kind of stuff. And the difference between Docker and Podman is like you can say like Podman is a much sleeker version of a Docker. Okay, and the core of the Docker is around the images, networks, volumes. These are the concepts which we know, and they come with a CLI kind of stuff. And then you'll say like you have to build, run and execute containers and building an image from your code base. So what you need to do is like your CI/CD pipelines is getting converted to code, and then Docker will execute it for you. And that is the architecture of Docker. Like, and Docker, in the Docker, what you are also specifying is like what kind of images you want. What is basically image means. What is a disk space, what is a network, what is a CPU, what you want for your container to run. So what kind of server. So basically it makes the life easy for the server selection of running it. Okay. Architecture of Podman is slightly different. It don't work on the central domain. It works on a CLI like Docker only, but it just runs like another program on a OS. Like if Nginx was under Podman has to run on the same machine, I can do it. But doing that same thing, Docker and Podman Nginx will run on the same machine, but Docker can overeat the CPU of an Nginx machine. So Nginx might stop performing when you have a Docker container is running with root. And Docker has an inherent problem of like security issue, like because Docker runs as root. If somebody is able to understand where your Docker is running, what kind of a structure it is, and then they are able to run a malicious script on your Docker file, it will affect your core machine also. It can go to a state where like it can even add a user to your core machine, which is like a huge security breach in case of if you are giving your service as a shared service, because the Docker, the problem is like you have to give it to one client because of the security risk. But Podman, in the same raw machine, we will be able to give it to multiple people because it doesn't have root permissions. So it will not affect any other privileges. It will be working only inside your image. And if I have to clean up, I just clean up the machine. So the only place there is a security loophole in this Podman setup is like, what are the shared services you are providing them? They can corrupt the shared services. So ideally, when we say like we want to deploy in Podman, we don't provide any shared services. The shared services also comes from your own another part, which has a disk space which is bigger. Okay. So our process of choosing Podman or anything is like it is 100% free. We can deploy it anywhere. We can also have like the compatibility of Dockers. If your teams is already building Dockers, they can actually easily convert their images into Podman images and then run it on our servers. So that wise backward compatibility is there. And Podman's like gives you a lot more security features for us. And then it also allows us to do host multiple clients on the same raw machine with the same kind of content as a VMware. So that is the purpose of us preferring Podman over Docker in our architecture kind of stuff. Okay. So the major concerns which I talked about is the pricing. So Podman is also built for enterprise. You can have your own version of hardware Podman, and then you can resell this whole thing to another person. So being a commercial organization, we would love to have that kind of stuff. So the biggest important thing which we want to do is like Docker registry. If you have to run on your own, you have to get permission from Docker. So we run our own Podman registry. So the Podman registry serves as like it's equivalent to having your own image. So the main Docker, like a Docker hub on your local. The Podman registry is nothing but a Docker hub on your local. So everything runs within your local. Even if you don't have internet, you still can have a Podman registry and then do deployments to your Podman cluster. So this helps us in terms of the mission critical scenarios, like if I have to deploy something for a police force or any kind of secure agencies where they don't want us to use anything other than internal to them. So what we bring in is like a Podman registry in-house and then a Linux domain, basically the package installers and all these, like you certify some of them and then bring them into a local ones, like local apt-get repository. If these both are set up, you can entirely cut out of internet and still work with this setup. So after you have done with understanding of Podman, you now need to start building your cluster, like Kubernetes cluster, open source containers. So most of you might be aware of Kubernetes clusters, so I'll be skipping it faster. If you guys have any questions, because these are standard ones, like so what we are doing. You can ask me any questions in the middle if you want to, or else we'll move slightly faster for this. Okay. So the Kubernetes cluster, what it does is like it has a master node and then it has worker nodes. Like once we deploy, it actually controls and then schedules it, and then the pods are the ones actually serve the final do the work and serve you the pages and what other work you are giving. So the crucial part of why we need to have this Kubernetes manager is because it will be a managed deployment for us. Like the load, if the load increases, it will increase, and then if the load decreases, it will decrease. So the Kubernetes cluster control panel, worker nodes, and then pods is control panel is the major ones which we will be seeing the clusters and deleting and all these things. But in general, we will not expose this control panel to outsiders. We will be using this control panel APIs to control the Kubernetes architecture deployments for us, like from a Jenkins or from our own prod kind of stuff. So we will be using the Kubernetes API server mainly to control our stuff, and then scheduler to do all these like things like ETL jobs and all these start and start workloads kind of stuff. So the control manager takes care of that work. So the node concept is what every developer, what is the biggest difference which I see from the college kids, why they are doing. It's like they need to understand what is a kubelet, what is going to be the node concept, why the node in the part is hosting, and then what it can do, what it cannot do again. So because this is what drives your how you can co-host so many applications in the same physical node comes from this node concept. So the reason why we wanted to have all our developers understand this node concept is because that's when you will be able to scale it. Like so, because the cost savings are very huge. Like if each node makes a 5% or 10% inefficiency, when you are running a 500 node, it will add up to 25-30 missions cost at the end of the day, which is equivalent to, if you look at like $3,000, $5,000 a month, which is huge, like 4-5 lakhs just in the excess, because if you're not controlling understanding the node concept. So the container runtime pod containers will be having. So everyone will have its own life cycle. Once the life cycle ends, you have to actually clean them up so that the resources are cleaned from the nodes for next set of like applications to take it. So because once if a node don't have buffer, then it will start spawning new nodes. Like you will need more physical machine. For us, for a data center like us, the criticality point is here is like we won't have too many access nodes. We will have very limited buffer nodes. Like it's not like AWS, we have like 30,000 machines on the same location. We have max like 20, 30 kind of stuff. Like so, and everybody understanding that concept is very important here. So this is where your developer will start coding. Like a pod is a setup where a developer will do container. So each pod, what people say is like, in the same pod, I can run a 3-tier application. Like you can run a database, you can run a middle layer and an API layer, which is like node, and then you can also do a front end and then say like I have a volume. So pod is nothing but your desktop, equivalent to a desktop, but you can run everything together. But what we say, we generally insist people is to like built one pod for one layer. So the pod should do only one purpose, which is like if it serves with APIs, it serves the APIs. It uses database from somewhere else. If it does serve front end, it has to serve only the front end. If this pod does only database, it does only database. So the reason for doing this is like it helps us in terms of horizontally scaling. If your database is choking, you have to only increase the number of database pods, not the API pods, not the front end pods. So the purpose of understanding the pods is to just making sure that the pods contain only single functionality helps you scale each one of them independently. Because all your underlying sharing, like what will happen to my database, do I need to change the URL of database and all, that will be taken care by Kubernetes service layer. So we don't need to worry about. So making your pod crisp and then do only one functionality is very important here. So the pod goes through its own life cycle of creation, running, basically its own life cycle. So this is mainly useful for monitoring a pod, what happens to a pod. So when you put a request for a new pod to the thing, it will go into a pending state. What happens to pending state is like till one of the physical nodes is able to host this pod, this will be in pending state. So when you have too many pods in pending state, that means like you are wrongly scaling your whole cluster. Like so you are getting bombarded by something. So pending state, the pod should not be in pending state for a long time. They should be very crisp, like maybe 1 minute or 2 minutes, where it is like setting up a new node like kind of structure. Like so that is a time which is needed as a reflex for your cluster to auto scale. So you have to configure your thresholds accordingly so that the pods, when how much time it takes for a pod to set up, that time you are giving. So another important thing in this pending state, like when you have a database recovery or you want to set up a complete server, which is like reading like 5 GB of data and then converting it into database or those kind of things. If you do it, your pending state will go for longer, like it will not come into a success state very fast. So that much downtime your service will get. So ideally what we say is like save your images in a state where it can be run within 1 to 2 minutes. So the pending state of your machines can be 2 minutes. Beyond that, it is something your cluster health is not great. Then you have running state, you have success state, and then you have the container pod completed its task. And a terminate state. Success state is useful for usually most of the tiny microservices will go into pending running and then you only terminate. But there is also ETL jobs. If you want to summarize today's sales and then send it as a report. After the summarization script is completed, you can say like succeeded or a failed state. After that, the pod will get terminated. So this is useful for pods which are coming up for some time doing their job and then they get die by themselves. And then there is also, if it goes to fail state, the Kubernetes will auto try to recreate and then reschedule. So this helps us in terms of daily nightly jobs. When the nightly job fails, you don't need to go because otherwise we have to go in the morning and then see like whether it is failed, then we have to retry it. So Kubernetes does this bunch of retries by themselves. Okay. So this is an example of Kubernetes pod YAML, right? So API version, what we have, example pod, Nginx container. So what we in the Nginx later. So it's like running an Nginx inside a Kubernetes is what this pod's example is. We will create different services of what we need. So, and then we can also specify image-based pods. So not only this is like a raw. It goes, it sets up Nginx container and then runs it in port 80 and then do it. This is a basic example. We will start doing customizing these specs for our own needs. So the deployments is what I'm going to now take into. So deployment of a Kubernetes resource is like managing an application state of pods, like replicas, configuration. So basically, definition of a Kubernetes deployment means it's not one pod. It's as many number of pods needed to complete a job. Based on their configuration, it can be 1 pod, it can be 3 pod, minimum of 1 pod and then 10 pods and stuff like that. And what we also need to look at is like based on the pod status, like running state, automatically handling failure state, and then scaling needs. So there is also we need to put pods rules when the cluster needs to auto scale, like CPU and memory when they go low, you have to spawn a new pod to handle the more requests. So that is what the benefits of the state gives you. And what it also gives you as Kubernetes is like it gives you a rollback very often. If you are making a deployment and if the deployment fails, you can roll back to the previous version of your images in the Kubernetes very fast. So the replica set and then pod templates is what will be very useful in terms of the high availability. If you are developing your pod like a developer, like you always check out your code, build your code, then run and start your container. That is not a production grade pod containerization. The production grade pod containerization is like you have your image crystal extremely ready so that if you start running a startup script, it should come up immediately without doing any kind of these kind of things. So those were being handled by pod templates, right? So each version of your code can be also pushed as a pod template after building. So that will help us in terms of rolling up, rolling down kind of services for the pod templates. It will also help you in terms of A/B testing. So when your main version of the pod like is running, like if Flipkart website 2.0 is running somewhere, now I'm releasing 3. So I will release in some Kubernetes cluster, the pods which will serve that. And some of the users will be redirected to this pod 3 from pod version 3 from the load balancer. So you will get those kind of controls. And if this user's metrics are good, then we continue deploying this pod 3 to everyone, or else we revert this pod 3's Flipkart version 3 to Flipkart version 2 in all the pods. So that helps. The replica set ensures it. So it's not one server in pod 3, it is like 5 servers in version 3, 20 servers in version 2. So that kind of a level you can do so that you can have a minimal base setup for you to test anything. So this I'll going to script like why use cases everybody knows like self-healing and all these things. We'll skip this. This is the use cases which we need for. So the pod deployment, and then these are the commands for deploying it, like use kubectl to deploy pods, and then check status for it. So the Kubernetes services is going to be the main important one, which will serve as our cluster. So there is an interpod communication which will be needed. So this is what we talked about. Like we have one kind of pods which are doing like backends, one kind of pods which are doing frontends. They both are communicating through the internal IP, and then they are mainly going to be Kubernetes offers the DNS. It's going to be resolved within your own network inside the Kubernetes, and then they will serve. Like but the pod B. The node in any one single pod A will not know what is there. Am I getting served from pod D or pod B? Okay, it will be taken care by the whole VNet configuration of the pods. Like so, one cluster doesn't know individual node of the other cluster. It knows only the full cluster. So it has to just get your communication mode resolved and then stuff like that. So the service to pod communication is what your load balancing happens. So when you get an input request into the Kubernetes cluster, so it will send it to it will load balance and send it to the pods which has maximum CPU, good health and stuff like that. So here we have a bunch of rules which will be needing for us to take care of, sending it to the least used request, round robin request, and this will also start doing in terms of the service communication. So for the end users, the users outside the pod, it's the service IP and the port. Inside the pod, they will have their own port, which will be node port, which will be communicating to the services. So now I'll explain you the scaling up process of the scaling up and scaling down. Like the new IP address comes in. So when a deployment happens, you have a bunch of nodes which are connected to a single IP and as a single service. Like when an update happens, one node changes the IP, it will update everywhere, and then it will start scaling up and then coming down again. So the rolling updates is the process of each node in each pod will get to deploy a new version of the code every time. And if if the deployment fails for some reason, there will be rollbacks, and then that's the deployment pieces of it. Scaling up and scaling down is like when your IP is getting enough number of requests or not. So basically your Kubernetes IP. Based on that, you can reduce the number of nodes or increase the number of nodes. So Kubernetes service monitoring dashboard is what we want to take it. So what is the different processes of monitoring like? So we have Kubernetes dashboard, which provides you with all the services. There will be service level metrics, there will be cluster level metrics, and there will be a machine level metrics, which will be Kubernetes will be going to you. Okay. But the Kubernetes dashboard is a separate service from the Kubernetes. Like if you guys want to manage it, then you need this service. Otherwise, you don't need to build that service. Like everybody doesn't need. If you have a fixed kind of Kubernetes service, you don't need it. If you want to share it across with multiple users and you want to monitor, you want to have a DevOps team which is monitoring these services, then they'll need this kind of stuff. So what you are giving this Kubernetes dashboard is like giving access to your Kubernetes master node, which will take the data and then show it into good graphs like this. And this can be exposed out to others if they need to. Okay. So hands-on we will cover after the LLMs part we have done. So these are the concepts. We will cover the hands-on in some time after we have covered the LLM piece. Like, do you have any questions on these concepts? And then otherwise we'll take you to the LLM multi-models and how we are running them in local. Actually, there is a question from Ritvik. So the load balancer which we are talking about here is like the load Nginx will serve as a load. Whatever we have done is like we have 10 or 12 bare metal machines and the network is connected to it. So rest of them are like software load balancer. On bare metal, what we have done is like we have installed virtualization services, which is like the Kubernetes clients and the Kubernetes masters and slaves we have installed and then converted them into kind of a virtual machines ready for Kubernetes usage. The load balancers, what we have is like they are all software load balancers managed by, it's a cluster of Nginx machines they'll serve us. Like we can have both hardware and software. Since ours is a mini data center load use case, we don't get into Gbps data bandwidths, right? So we can handle, because most of our machines comes with 10 Gbps bandwidth, and then the bandwidth which we send out from the data center lease line is like 200 Mbps. That is handled by a 4-core decent enough Linux machine with Nginx will be able to handle it way better. So the only place where we will get choked is on our local LAN. If you are transferring TBs of data, this load balancer will not be able to handle it immediately. But that is a very rare case, like when you are transferring a DB to DB. So the load balancer which we are talking about is like, these are all experimental software load balancers. Hardware load balancers are there for larger clusters. The other ones, like which you the bare metal environment, the master failure is what? Like I will share you the screen for it. On our second screen, like, are you guys able to see my screen? So the first architecture which we did is the first mission which we missed in it. I'll just go back there. So this is an active backup for the mission gateway. So when you look at it, like this is a gateway mission, this is the Nginx. If this hardware fails, the static IP will start pointing to this active backup, and the active backup will be connected to all these physical machine Kubernetes and NAS the same way as the gateway. So it's an exact replica of the machine running on a different IP. So when this IP, local IP 6 or 7, whatever the local IP is, like 192.168.1.6, it fails, the static IP will be mapped to 198.168.7. That will be, this is active backup. In this active backup, we will have the same load balancing configuration as the previous one. So our network will run smooth. So we don't expect two machines to fail at the same time. The Kubernetes cluster has a problem of master node failure. If this master node fails, that cluster will fail. So that's the reason why we have isolated Kubernetes clusters. But the advantage is, like, since we have multiple Kubernetes clusters running in the data centers, if one fails, but it will need a manual intervention for somebody to initialize the Kubernetes cluster on the another set of raw machines. This master node is failed. So we have to get another master node or another cluster with the similar kind of worker nodes and master node to run this service. So the problem which you pointed out exists in Kubernetes cluster, not on the gateway. Okay. Any other questions, or else I can switch it to the. So I think I'm continuing with it. So let's start with, like, this is, you now know this data center can handle basic services, websites, APIs and stuff like that. So now let's come to how are we tried running LLMs and multi-models in our local setup. Okay. The objective is to set up a research lab, like in a educational institution or companies where people want to experiment with machine learning and then large language model solutions on their own, like they want to try it. So the local data center, what we said is like we'll do a 10 server kind of a cluster, and then we will have Kubernetes to efficiently orchestrate it so that load balancing, all these concepts are there. Then you have running an LLMs on a GPU machines, like the GPU machines has to be a shared resource. So then since we have this other two things set up, like local data center and Kubernetes setup, we want to introduce the GPU machines into it and then see how we can get our performance out. So these are different kind of like machine rack layouts and then poolings and stuff like that. If you can see the camera, show the backside, I'll just remove the blur and show you guys that I'm sitting in the same place as so this backside is our data center. So we have all these 10, 12 machines, the LLMs, everything is running from the same rack. So the rack costed me around 10 to 15 lakhs and it is in my home office, guys. So just for your reference, like, and this office, this data center runs LLMs. So you can see what we have, how we have reduced our need for a lot of stuff, right? So the power cooling layout, and so what is an effective need is like your CPUs and then your power and cooling system, the UPS system has to handle your 10 machines, and then the rack layout. So this for 10 machines, this kind of a small rack takes care of it, everything. And then we have bought NASs to support large data sets. Okay. So now let's get into the GPU machine for LLM purpose, right? So even if you, so the GPU machine which we have is like, we don't have the very powerful, the NVIDIA 490s and then stuff like that. We have the smaller gamer NVIDIAs like RTX 230 kind of stuff, which has 16 GB RAM and then 2500 performance cores, which is useful for kind of enhancing your image generation in Photoshop or animation generation, those kind of workloads, it does well. So it's a commodity hardware. It costs you 50K and the machine will cost you around 2.5 lakhs. This is not like the very high-end GPU machine which we are talking about. In this, you cannot train a model. You can run a model, you can train RAGs. You cannot train a full LLM model here. So in the previous lecture, they were saying like the full LLM model needs larger machine and then larger setup and stuff. But to take advantage of the latest LLMs and then building your application RAGs on top of it and then using multi-model models to improve your solution is what we are going to cover. We are not going to cover like, will I be able to create a new Llama version by myself? This LLM machine will not do it. But what it will do is like, take a Llama 3, update it for physics 11 standard or physics 12 standard, one of the problems which we are solving. And then when you ask a question, it will respond it back. So that is the purpose. Ollama is like it's basically, it helps you to install multiple LLMs on the same GPU machine and then switch between them runtime to test them. So Ollama is nothing but, it's like a web server like Tomcat or any kind of Apache. You will be able to run, with Apache, you will be able to run PHP, Python, Node, anything in the backend, right? Same way Ollama is like a setup for LLMs running on your local machine. It can run any LLM. It can run DeepSeek, it can run Mistral, it can run Llama. It cannot run ChatGPT because they are not, all the open models we can run, whichever is available in Hugging Face. Okay. So the storage, what we need for this machine is like, you need a good GPU and you have to have a decent CPU, which is like 8 core or 12 core kind of CPU. And you have to have all your libraries installed properly, TensorFlow, Python, PyTorch and all these things. And then you have to have a 500 GB to 1 TB SSD machine for your model to expand, because when you download a 7T model, it expands into 24 TB kind of stuff and disk and then runs. So you need that much high speed disk If it happens in hard disk, it will be slower for you. So we would recommend 256 GB to 512 GB of SSD in the machine, and the main model running from there. Okay. So next comes like once the model is set up, we need a UI for it to experiment. Like the Open Web UI is nothing but a ChatGPT responsive UI. We can install the Open Web UI in our own one of those machines in the Kubernetes cluster, and you'll see like what it is there. Once you have the Open Web UI, you will be able to select which model you want to use it, and then you will start RAG training them. So Open Web UI has internally LangChain. LangChain helps you add your own information to the LLM, and then LLM will start responding as if it has read those books or those texts separately, and you will be able to fine tune its performance by doing prompt engineering and stuff like that. So the most useful solutions of RAG are enterprise search, chatbot in real-time question answering, and those kind of stuff. So we will show you an example of how we have built something in Open Web AI in terms of this custom RAG area. So why we prefer a GPU machine versus CPU machine, right? So CPU machines generally get into the serial processing. Based on the parallel processing capacity of your GPU, it can go up to thousands of cores, like optimized for deep learning. So affordable, and so CPU machines still you will be able to run your LLM and then test it on your own desktops, like even without GPU. The only thing is like the response times will be slower, and the other ones like the GPU machines are needed for training and large scale infrastructure, and then also production infrastructure. So you'll see. So the optimized AI library is there for like NVIDIA CUDA TensorFlow, and Apple Metal are optimized for basically. Apple has a poor optimization in terms of the GPU, so which we have to see. Like we have compared it against Mac, but NVIDIA ones are the GPU bandwidth and memory is efficiently configured. So if you look at the GPU performance versus CPU performance, like most of your performance are like DeepSeek and then Llama, and the same questions are asked in a CPU machine, which is 16-core CPU versus an 8-core CPU with a GPU. You see the difference, like the performance is half or like 1/4, like from 12 seconds it has come to 4 seconds. So we found that this particular segment of 4 to 6 seconds is a good application level for us to start responding to users in a task, like in a non-real-time tasks, like generating a content for somebody, generating a report, and those kind of things. So we have to increase our GPU speed further, like 3 to 4 seconds is good enough for the web UI. Only Mistral model works on that range, like DeepSeek is still slower. Llama is kind of the same performance, but we have to bring it under 3 seconds if you have to really do a chat. This is good for applications like where you are asking some help and then there is a suggestion coming in, or you are asking it to generate some text, it generates and then puts it for you. Okay. So we tried running LLMs on different platforms. We said like, why do we stick to only NVIDIA GPU? Everybody says NVIDIA, why not try it on Mac? So the Mac has a problem of Mac is still a desktop level. It's a laptop efficiency, like it has only 80 GPU cores versus NVIDIA has a large number of cores and then stuff like that. So what we used NVIDIA is not this one. So the ideal ones is like getting one of those 2 lakh ones will actually is good, but for doing chatbot kind of an application. But this whatever the NVIDIA 230 RTX is good enough for doing all the other applications. You can have 5 or 6 of them in the same cost as a 490. So it's a mix and match of applications, what you want to build and what you want to scale. Okay. So these are the actual steps to run an Open Web UI on your local, and then when you have a Ollama in place, you will be able to download and then test these models yourself. So RAG setup you every enhances accuracy. So what is the purpose of RAG is like you pre-train your model on the text which you want the model to answer perfectly. Okay. So it's like helping a user read a book and then answer from the book. So he'll be more efficient if you ask the questions only from the book. Same way, the models will be performing better if it is already read the solutions and the books. It's useful in terms of a learning models, like in an educational institution kind of setup where schools, colleges, the content is very fixed. and you want, and it also doesn't do hallucination, and it will not do talk something completely outside the text and stuff like that. So this helps us in terms of a safe LLM for kids as well as the learning materials. So we were fine tuning ourselves in terms of the RAGs. Like, so what we have done in our collection is like question. So we were running a edtech website from our data center. The edtech website caters for NEET aspirants. So what we have done is like NEET chapters, NEET mock tests. We have trained them in different kind of things, and then all of our benchmarks comes from those performance numbers. Okay. So if CPU may 15 seconds, when you use GPU, it's 5 seconds. So all these comparisons are here for you to see, and then we have worked on it. So the model comparisons like DeepSeek versus Llama. Llama 3 is what is very better performing in terms of the models compared to DeepSeek and stuff like that in terms of the solutioning and then answering the question in the right way. Okay. So what we are up to building is like we build an AI powered NEET question paper generation and then doubt clearing session. That's the application we host in this data center. So if you ask about any of these APIs and then questions, so what we have done is like building an doubt clearing teacher, simulating a teacher in a multimodal model. So what we have done here is like ask a question in the audio. The audio is converted to text and then passed on to the LLM plus RAG. Then once the solution comes back, we have taken it back and then converted them into images and then do it. So this is our architecture. Like, so when you say like web speech recognition kit, which is Google's speech to text, we converted, send it to the model, Mistral, DeepSeek, Llama 3, different models. We use mainly Mistral and Llama 3. Convert them, once the API response comes in, we send it back to Google's text to speech to convert it to MP3 audio. And we also send it to image generation platforms like PPT and images, merge them to create a kind of a 2-minute video for an answer the solution. You can see the video and you can text it out. So that's the idea. So if you look at one of
the electric field inside the sphere, x less than r, is directly proportional to 1x. 1. This is because the charge density is uniform, and the distance from the center increases as x approaches r. So, the correct answer is 2. 1x.
So basically, some of them slight differences are that what we were trying to do is like real-time voice-oriented doubt clearing session, because the kids, what we feel is like when they see voice, they engage a lot compared to an MCQ and ask them to read a lot of content. So that is a purpose. So we wanted to create an AI doubt clearing teacher. So this is an API code for it, and then how it works, kind of a demo for you guys. So NeetBot is another website which we said like when you paste any question, it will give you answers to it. So that is a kind of a solution we have built. And infrastructure setup wise, like what is the summary? The infrastructure setups, we have got a full stack. With our own infrastructure, we are able to deploy databases, APIs, full stack services, GPU powered AI models like S3, like the AWS and Google Cloud or any equivalent clouds in that matter. Like implement monitoring solutions and cluster health resources similar to what is available on the paid services kind of setup. Then what we have, the next takeaway we are able to run LLM models on much smaller gamer kind of a GPUs to get a real life application, and implementing deploying web UI RAGs and then this one. So key takeaways is like Kubernetes based AI cluster providing. So you can build a reliable solution on your own with Kubernetes, so that even if it is auto scaling, number of students comes in high or low, you will be taken care of. And the tools like Olama, RAG, OpenWebUI are very user friendly in terms of taking away. So now let's stick to a workshop. We have a real time workshop for it. Can we make Yogesh, you are there?
Yeah, is it audible?
Yeah. Can you make Yogesh the presenter? You have the code for setting it up, like the server setup and then how things are working for us. Demo.
Okay.
I'll stop presenting on my side.
So my screen is visible?
Yeah, the screen is open.
Okay.
So, Yogesh, you can take them from the deployment process, or you want to take only the question answering part?
I'll just explain what we have built, like that this thing, a multi-modeling basic thing, and I'll show you demo of that open web UI, how that knowledge is we can create that knowledge.
Yeah, sure. Go ahead.
Okay. So this is like a basic multi-model we are trying to build. So as of now, we finished until like we can either give the input of the question in both ways, like as a voice command or as a directly typing and subject, which will get the response like from the model that we are choosing, like Mistral or Llama 3 that we are currently using. So let me maybe we can ask something like. Can you explain me what is stock notation? Okay.
So the mic is connected to the Google TTS, and then it brings the text here, and then once you submit it, it goes to the next stage.
So we got the response like this thing. And the thing is like it also from the response we also get that what that MP3 audio. Like let me play it. So this one. So here, while taking the speech input, we have used for client side, we have used WebKit speech recognition. In the back end, we are in the plan of using ASR kind of models, but here for playing this response, we have used that GTDS, Google Text to Speech, that one. And so this is how that open web UI looks like. So we have done for many testing here in the workspace. We can see the knowledge. So this is the area where we can able to give knowledge like rack setup generally. So for example, if we take this neat NCRT chapters, I have provided two PDF. This is like the summary PDF of the chapter redox reaction in the NCRT level, and this one is like I think redox reaction from same NCRT. So based on this, we can able to ask questions, so it will give us the answer. So if we compare with the RAG and without RAG, you can see the how this actually works. So this one kinetic theory, I have one question. I asked one question. Okay. So this is like there is no RAG attached. It is like a generic thing, generic response. So if I'm comparing this one with the RAG that we provided, now it is like much more plain and clean because it is referring to the context which I'm provided. That is like the summary of the PDF. So like we will use this RAG on top of this model to make it more efficient. And
So Yogesh, the model, the tags are selected in the API directly. Like you can have multiple versions of this chatbot with a different backend tags. Like.
yeah, actually.
So, guys, the Open Web UI is like your own internal team's testing toolkit. So, what is the
Yeah.
API exposing it out is what you have to build further for. This
basically they provide API access for all the models that which we want to use. Then we can fine tune these models and we can train these models and we can use it on our own website, like how we try to building this one.
Okay. Guys, any questions on this RAG training and then stuff like that? So we will love to take that. Then Pradeep will explain the Kubernetes cluster deployment setups on our local data centers.
Having a Kubernetes cluster which is like only having a master node and a worker node. So maybe I can show you. So you can see like I'm having a master node and I'm just having a worker node. So I will be like showing you a demo. Like, so the service which Yokesh showed you is like already hosted. So it is like hosted in a domain name. So I'm just asking a question over there. So right now the backend services is running in the Kubernetes. So I'm just asking a question over there. You can see like the responses is coming. So the backend is up and it is running and it is serving from the Kubernetes cluster. So right, I'm going to be like stopping the pod and I'm going to show like how it is going to be like breaking over there. So right now the backend is like in the status of running. So I'm going to be like stopping it. The pod is getting deleted. So now the backend service will be like not working because it is being served from the Kubernetes cluster. Yeah, it has been deleted. So I'm just going and getting. So I'm just hitting a message like hi. So in the network tab, you can see like the things are breaking over there. So then I'm again making it up. Now you can see the status like it is running. So now the backend is up. The status is like running. So that denotes like the backend is like healthy. So I'm just again making a call to the backend. So now you can see like there is no error and the response is coming. So it clearly demonstrates like the backend is served from the Kubernetes cluster. So as sir was like showing in the PPT, so I'll be like showing you the. So these are like the configuration files. So now it's being like the server is like doing all those load balancing jobs. So what server was explaining the Kubernetes concept. So now pod is like running a server over there. It is having a dedicated environment over there, and what server is doing is like doing all those networking sort of stuff. It will be like load balancing. It knows only like the name, the label will be like mapping over there. So it will be mapping over this thing. So whatever it is like, if let's say the status is like running right. So what if it is getting crashed? The IP will be like keep on changing, but at the point of time we don't know what will be the IP of it. But if you're like running it through service, so the service will manage those IP addresses and it will be like mapping the pod to the service, and then it will be like doing all those network communication. And also service will manage all those things. Let's say right now I'm just demonstrating, so we are having only 2 3 people, so like opening the sites. What if we are having multiple peoples? Then comes the deployment part where I need a minimum replica of like 10 machines, like 10 backend servers running on to it. So in that case we will be like having a deployment file over there. So where we will be like mentioning like I need a basic of 2 replicas. 2 pods should be running, 2 backend service has to be like active, and then it should be like listening to it. So everything will be like managed by the server. So based on the label, so I'm having a selector over there. So this will be like mapped to this. So the name or all same. So it will be like mapping to it. So on the rollback, role updates, everything will be like managed by this deployment. Let's say tomorrow I'm having a different image. Let's say it is like pulling from our own registry. So now tomorrow I'm just making a deployment and the image is like the tag is like latest. Now the tag is like version 2 and all. So now I have to be like changing the deployment file so that I have to be like putting the new image over there. Then the rollout happens and everything will be like coming. Then the changes will be like over there. So we will be getting the recent code and it will like manage. Let's say we are having 10 pods running over there, it will be like without downtime, all those will be like rolling out and our new changes will be like deployed over there in the Kubernetes cluster. So this is how the Kubernetes like internally doing its stuff. So yeah.
So this is about local Kubernetes, how Pradeep is running and stuff like that. So we had, so basically, guys, so Pradeep and Yogesh are 1 year experienced engineers just last year, and then within a 2 months time frame, they have set this whole entire data center for me in terms of getting this right, and then it's simpler to get them right. And just a second. I got a question from someone like, so in the RAG model website, so the RAG model website, since they are making an API call, the models hosted there are using any pre-hosted website? No. So the RAG, what they are using is like, what is hosted is the model is hosted in our own Llama. Pradeep can show you. Pradeep, can you share your screen and show whether in which machine the Llama is running? The Llama, Mistral, everything is running on our own local machine. The APIs are getting called, it's just the structure of the code between the two part separation. It's all local host calling. It's calling within the network. It is not going outside. So the Google TTS is the only one which the web browser already provides by default. Rest of the ones, all those LLMs are hosted our own. These LLMs are not our own. It's just the standard LLMs. The RAG, what we trained, is stored in our own data set. Like, so basically we downloaded the LLM from the internet and then running it in our local. So whatever the RAG improvements we are making, it stays with us. So TTS agent, there might have been, we thought has more natural tone voice to it while reading the response also. So there are multiple TTS agents which are under the works. So we will, so what it does is like, since it's a lab kind of a setup, so if you look at us, like we have said, like, so the MP3 generation is a block where we can do OpenAI's Whisper tomorrow if I have to use it, if it is paid once. If I have to use any of these third-party guys to generate these whispers, I can do it. Like, so right now what we have done is like, we want to demo, we built a demo multi-model setup, like that's it. Like, so when to improve your voice, you'll still see like there is a speech API, there is a company which has much more Indian voice to it. Like there are models which are trained for Indian voice and then doing stuff. So we can keep modeling, changing it. So the most of the models which we try to do is all hosted. So whatever we have demonstrated is all hosted in our own data center. So we don't need to go outside the network for it. Okay. It is possible. So is it possible to mix local models and APIs? I have guided another project where what we do is like we do a local RAGs response, like, and it gives you, basically we instead of the open, see, this is LangChain as a RAG we are using in this experiment. There is another experiment where we use Elasticsearch as a RAG for searching hotel entities, activity entities, and then bringing them text backs. So what Elasticsearch gives you is like objects. It's like e-commerce or a might make my trip kind of an object. So to convert those objects into the real text, like the most of these Llama models and all are not doing good. Like ChatGPT 4 is way better than all these models. So this part of LLM is running locally, getting this model, combining the text, and then rephrasing the text is again another time we are going into ChatGPT and then bringing the response, because we want to respond in a chat size, like you want to respond within the 4 lines and it has to be crisp and then precise. So for that we can use. So the only thing is like it's about the cost. Like you can have whatever working locally well, use it. If something is not working as per the quality, for that one alone you can call the external API and use it. So what it builds you is like a testing ground for students and young engineers to test this. Like, so what we are built, so our aim for this project is to build this as like lowest cost possible. So what we have done here is like we spent around 20 lakhs and then build this, and then within 4 months, we have reduced our cost. Like, so we were building these LLM models and then testing them on different sites, and then different projects were using it. So for that, we were spending around 2.5 lakhs every month. So now 50% of the cost is recovered in just 4 months for us. Like, so whatever we spent, we have saved around 10 lakhs in terms of the server cost if we have to run the same set of things in AWS. So what is the most important takeaway which I feel is like for education institutions to take up these kind of projects, because nowadays after AWS and all came, nobody is having local servers much. Like everybody is saying like and what is the difference between a learning on a web browser kind of environment? Like if a guy learns coding from HackerRank kind of things, he will only learn that kind of stuff. So a guy learning it on the real environment and then deploying his own code and then seeing them performing and deploying his code along with 4 other students working on a different module, and then how the APIs interact with each other. So those are the real life trainings needed for a engineer. So what we have built is like our own training setup for our freshers. So that is the major focus for us building this ecosystem, and also helping them in terms of, we have a couple of customers in our own friends and circle. We have a couple of customers in EdTech, so they will be using these models for their own internal needs. So what we have built is like POCs around them. So by doing a small spend, like, so we will be definitely spending in terms of desktops and lab machines. Like it's as good as like getting 20-30 lab machines putting together as an ecosystem where it is in the cutting edge setup as close to AWS cloud providers as possible. That's what we were trying to demonstrate. And in our demonstration, leaving that GPU piece, like the highest for training an LLM, everything else we have achieved is as par with the industry standards. So that is the thing. So if I'm able to match every service by service as AWS, I'll be able to do. Only thing is like we have to put some engineers to build it. So whatever we have built is basically needed for us to demonstrate everything we can build in-house, and then you can host it. And it's a training environment. All of these services are open source. None of them we need to pay royalty or anything. Like it's just pure joy of learning these things and then building these things and then building our own solutions for our own community needs. So that is the purpose of we doing this exercise. So and why in deep learning, why did I present this? Like I could have presented something else, which is like chatbot for travel and all those kind of domain specific trainings and stuff. So we wanted to present it so that tomorrow you guys can take this to your education institution and then start building similar projects, because the scale of the project, the cost of the projects are very small. You can start it as small as 3 mission cluster, like our 5 mission cluster. So 5 missions maximum cost you around 10 lakhs. Like with that you can get started, and with a basic static IP and internet will cost you around 5 to 10K a month maximum. That's the only cost you will get. So with that you can get started, and then the students and researchers can get involved and then start building further. So when I used to study in IIT, we don't had this AWS kind of stuff. So every lab is built by us, hardcore. Like so, I was maintaining the website of the lab, and I was maintaining, a couple of friends are maintaining the email services. Now that culture is gone because everybody is reliant on Google, and then web service means you'll do Lambda, AWS will do this, that kind of stuff. And also even the nowadays lab coding is moved to websites like the training websites. So that is where the shift needs to happen. The students have to have real life hands-onness of things. And I realized that they are not having it because we cannot replicate AWS equivalent to on our own. So we decided to do it as a project. We started it around August or September, and we went live in September last. And we completely shut down our AWS cluster within that month. Before that 6 months, we paid like almost like every month we are paying 2.5 lakhs. Like from June to September quarter, we paid around 7-8 lakhs to AWS and GCP together. We are a multi-cloud company. But now this whole thing, we have never paid anything. It's all serving from us. And then the reliability we got is like the downtime is only 30 minutes, and that too because of the power outage kind of stuff. So any questions on this, guys, any possibilities which you want to ask or anything, I'll be happy to take it. So it's basically to inspire people to build their own equivalents of AWS and GCP.